Okay, it's 10 o'clock. I'll get started with the presentation. Cheers. So welcome to my presentation on FPGA accelerated computing with neural networks. Okay, didn't respond for just a moment. So the scope of this presentation is mainly going to be the FPGA computing aspect itself. So using the FPGA to do computational tasks rather than a CPU, and sometimes looking at data that is better processed on the CPU rather than on the FPGA. Other things are interfacing to and from the FPGA, so how can we optimize that communication, and some design considerations when doing this. What is not in scope is the actual usage of neural networks. So I'm not going to discuss on how to use neurons, what activation functions to use, what optimizations to use, and so on. That's way too much for GLA, and especially to do in 15 minutes. I think I will bore everyone to death. Well, who am I? Well, I'm Natan Biesmans. Well, I'm an FU architect. Used to work for National Instruments as an application engineer, so I might have helped some of you, maybe annoyed some of you. Currently, I'm a LabVIEW R&D architect at Qblocks, and I'm working at ASML as a lead engineer through Qblocks. This presentation is going to have a couple of different chapters. So the first part is what is computational acceleration. Then we're going to discuss the computational offloading. So offloading computational tasks to a specific piece of hardware, in this case, either the CPU or the FPGA. Next up, we're going to look at scalability. So how can we optimize our code for the hardware we have, for the computational task we have? How can we do this? So computing acceleration, what is it? Within the context of this presentation is choosing hardware based on the task you're doing. So most of the times your computational task is going to have certain facets which are more important than others. In this case, I made this little Venn diagram, which you might find interesting, on what to do with your computational task depending on what's important for what you're doing. So for example, if you're using floating points with a lot of parallel usage, then GPUs are the best way to go. Then look at CUDA cores, CUDA processing, and so on. If you're looking at more asymmetrical and parallel tasks, then the FPGA is the way to go. So asymmetrical means doing a lot of things at the same time, but it's not really the same task. If you're looking for more asymmetrical and floating points, then most of the times the CPU is the best way to go forward. And most of you are already using this as, for example, producer-consumer loops, where each loop is doing their own little thing, or actors where each actor is doing its own thing, which is most of the times completely different than the other actors. So let's focus within this presentation on FPGA computing. So FPGA computing is, well, mainly focused on parallel tasks. So either doing the same thing at the same time, or a lot of same things at the same time, or asymmetrical tasks, doing a lot of different things at the same time. One of the downsides of FPGA computing is floating points are, well, they eat up a lot of resources, so don't use them that much. The extra benefits of FPGAs, or some of the extra benefits of FPGAs, are, well, they're deterministic. Like already said in chat, they work, they can give you a result within nanoseconds, or at least consistently give it to you at certain time intervals. Also, most FPGAs allow you for direct I/O access, which sometimes can be useful, especially when you have sensors to interface or outputs to interface to. And also, they can be really flexible. It's just a programmable silicon, so you can put a CPU. You can put a CPU on the FPGA. Think of picoblaze or microblaze. Very interesting subjects. It's also, again, not within the scope of this presentation, but definitely something to look for if you're interested. Now, why would you use it? This seems like both something really easy to understand, yet why suddenly adding this this GLA? Well, what's currently going on is there's quite an industry shift going on. Mainly, last couple of weeks, Xilinx has been bought by AMD, or well, it's still going on. And a year ago, or I think even longer already, Altera was bought by Intel. So these are two big players in the CPU market, and they're thinking of adding FPGAs to their lineup, even within the CPU. For example, Intel is already looking at putting FPGAs in their Xeon chips, so that data centers can add FPGAs to it, or use FPGAs natively. Also, VHDL used to be the default language, but nowadays we, for example, have LabVIEW, which really nicely adheres to the FPGA frame of thought, doing things in parallel at the same time. Now, when would you use it? Well, it's a new field. It's been around a couple of years, but lately it's becoming more prominent now that FPGAs are becoming more powerful, bigger, and well, the big leaders are supporting it. There's more research going on and stuff like that. So currently, big data is one of them that just pops in mind straight away. Timing constraints. So if you need an answer straight away, well, FPGAs are the best way to go forward. And also if you have limited processing power. So let's say you have an underpowered CPU, but from time to time you have to do something really intensive. Well, then you can put it on an FPGA, and when you need to do an intensive task, you load in the bit file in the FPGA, do your task, get the data without waiting an hour, a couple of minutes, seconds for that piece of data that you want straight away. Like I said, it's a new field, so try to see how this relates to you, see what can be interesting for you. You can already ask it in the chats. If I deem it relevant, I'll answer it here. Otherwise, I'll move to the breakout session or to the Q&A after this presentation. Now, why did I start using it, or how did I get into it? It all started with a question. Can I put neural networks on an FPGA? I mean, it seems straightforward. You have neurons in your brain. All of them are working at the same time. And that's pretty much what an FPGA does. Can I make that work? That's the question I start with. Well, out of that question, when I started coding, trying out little things, I started looking at, well, the FPGA has certain limitations compared to what neural networks conventionally need. Neural networks are normally really floating points dependent. Most of the times they're quite scalable. They tend to change over time. How can we leverage that to the FPGA? And after that, I started thinking, okay, now that I know these limitations, I found workarounds. How can I optimize neural networks for FPGAs so that they use less resources so that you can put bigger networks on your FPGA, or use limited resources, so a small FPGA, to actually be used by larger networks? How can we split that up? Well, the results, well, you get it from you're gathering it from this presentation. I can now generate neural networks for FPGAs with optimizations using custom algorithms. And well, two of the results are two demos I made for you: an adaptive cruise control on neural networks on the FPGA, and a traffic light predictor. So that was, well, what is computing acceleration? Now let's discuss computational offloading. So first of all, we're going to discuss offloading computational tasks from the CPU to the FPGA. We're also going to discuss data management, so how can we transfer data efficiently to and from the CPU, to the FPGA. And also we're going to look at certain scenarios where we actually want to use the FPGA, the CPU, as a co-processor for the FPGA, which suddenly reverses the way we're normally using the CPU. So first of all, offloading the FPGA, offloading to the FPGA. So within this graph, or well, this example, this arrow mainly focuses on computational tasks itself rather than the data flow. So most of the time, or most often when doing computing acceleration, you'll do these three steps. You load the data to the FPGA, you do tasks, computational tasks, which are heavily optimized for the FPGA. So again, think of our massively parallel operations, operations where timing is absolutely crucial, or, and this is actually the biggest benefit of FPGAs, well, large sequential data sets. So our CPU, it can just push data to the FPGA. The FPGA will just take it, it will process it, and at the same time it's coming in, it will push data back to the CPU saying, hey, this is the result, do with it what you want. And so that's also the last step, load data back to the CPU. As a nice introduction, nice demo, I have an adaptive cruise control example for you. Now, I do want to point out, I wasn't able to source a MyRio in time for this presentation, so it will be a screen capture. However, during the next slides, we'll go through part of the codes to see, okay, how does this work? How does that work? So here I made a little piece of code in hyper-realistic 3D environments with two cars that, well, one you can control. This is also available in the demo code. I will post a link. We can control the follow-up car, or well, the front car. We can say accelerate or deaccelerate. And the car in the back is responding to, well, the car in front. Now, what's happening here is, or well, when this was created, everything was running on a MyRio. So this interface is just a HMI. But all that was actually happening was the HMI was passing it on to the CPU. The CPU determined what it was supposed to do with it, either pass it on to the FPGA or handle it in another way. The FPGA looks at the data, in this case with a neural network that's on the FPGA, and passes this back to the CPU. In real life, you won't have this HMI. It's more real-life sensors, but it's a nice little demo to show you how it works. During the next slides, I'll go into it more in depth, but in the meantime, I can already show you a bit what's going on. So all in all, we have two loops on the MyRio. One is just gathering data from the FPGA and passing it on, in this case, to the HMI. While the other one is processing data coming from the HMI, either determining if it needs to stop, and also gathering data from the HMI. So if we have a change in acceleration that we ask from the car in front of us, then we can respond to that. So in this case, it looks a bit like this. So we're gathering the data, we're compounding it, and we're sending it to the FPGA. No worries about this. For those of you who are not familiar with FPGAs, I will go into more depth on this in a moment. And for those of you who know it, don't worry, I'm not going to go way too far with this. So this is what we're pretty much doing. And then in the background, we have some code running, or in the FPGA, we have some code running, gathering data, sending data to the host, gathering data from the host, and this, well, is our neural network that was automatically generated. So for those of you who are interested, I'll, for example, show a neuron. So it's just multiplications and additions. If you have more questions about the neural network side, please leave them for after the presentation. Okay. So next up, let's start discussing how can we efficiently send data from the CPU to the FPGA and from the FPGA to the CPU. Some of you who have done the FPGA courses will already look at this and scoff, but maybe you'll pick up something that you missed. And for the others, this might get interesting. So one of the most important parts of large sequential data sets with a processing unit that can handle a lot of data is, well, we need to be able to push data as fast as we can. Now, in the past, we had to make apartment structures with codes. So we had one loop or a thread sending data, the other thread was getting it back, but it was all within the same CPU core. Nowadays, we can actually take more control because we have multi-core systems. So we can actually take control of the cores themselves and say you're going to do one task and one task only. For example, in this case, core 1 is going to send data to the FPGA. Core 2 is going to receive data from the FPGA. Core 3, maybe some offloaded tasks. We're going to discuss that in a moment. So that's when the FPGA sends a computational task to the CPU. And core 4 can be something else, either the operating system, your emails, Google Chrome, watching some YouTube, can be what you want. Now, LabVIEW actually allows you to do this quite easily, locking a thread, saying, okay, you're going to do this on one thread. And that's with time loops. For those of you who have done the LabVIEW performance course, it's going to sound quite familiar. What we're doing here is we're forcing specific operations on a core. The benefit of this is, well, we have no context switching. So a thread is not suddenly going to switch from one CPU core to another because the operating system deems it necessary. One of the benefits of that is, well, you're not going to have gaps between your data set being pushed to your FPGA. And the other one is, well, there's less overhead because when you do, or when there is a context switch, you're going to have a gap of computational tasks where the operating system is doing tasks. However, well, it's already stated here, don't overuse this. You can get something called lockout, which means all the CPU cores are doing their thing, and you suddenly want to say, for example, stop, and the CPU won't listen because it's doing exactly what you told it to do and nothing else, because all the cores are busy. The other one is resource starvation. So maybe you are using 3 of your 4 CPU cores or 7 of your 8, and you have this one core that's trying its best to do whatever it needs to do, but it's just not cutting it. Suddenly your operating system is going really slow, or Python is doing an hour on something that used to take a minute. This can happen. Oh, that reminds me. So going back to the code here, so in this case, I have 2 time loops because my Rio has 2 CPU cores. One of them is dedicated on gathering data from our data source, in this case the HMI, and sending it to the FPGA. And the other thread is just solely focused on getting data from the FPGA and processing it, sending it to the HMI in this case. And as you can see here, I manually dedicated put in the processor. This is not really a scalable way. There are ways to create your own algorithms to look at how many cores are available, how much is your CPU usage already, to then allocate cores dynamically at startup. Next up, communication. So with FPGAs, we have multiple communication sets, but I'm mainly going to focus on tag and DMA. So tag is, well, I like to think of it as the equivalent of a local or a global variable. So it's just you put data in it, and whenever you want, you can read it. That's pretty much it. So it retains the latest value. Of course, it's lossy, so if you override it and forgot to read the previous one, you lost the data. And it's mainly focused on the FPGA front panel objects. You'll get used to this if you're working with FPGAs. Within the code, I'm mainly using that on 2 places, more as a demo at this point. I'm asking the profile ID, an identifier I put in the bit file, or in this case on the hardware code itself, to see, okay, which bit file is actually loaded. This is something that's going to pop up a bit later in this presentation again. And the other one wasn't really necessary. It was just to say stop the loops. I know for FPGAs it's normally not necessary, but it's just to show that we can both read and write to and from the FPGAs with just this lossy format. Next up, we have DMA communication. So DMAs, well, they're queues. It's just a memory space, and you can just push in data, and whenever the FPGA feels like it, it'll grab data out of it. And also the other way around, you have a memory space, the FPGA can just push data as fast as it can in it, fills up, and in the meantime, the CPU can take the data whenever it has time to do things. So it retains all values. Of course, this is with an asterisk. If your data or if your memory is full, well, you can't add any more data. Then you really need to grab data from the memory. So limited size and also limited amount of channels. So this DMA, direct memory access, depending on the FPGA you're using and depending on the system you're using, you're going to have 4, 6, 8, 10 of these channels available that can work in parallel. So if you want more, then you need to look at different hardware resources or looking at how can we combine these, which is also something I've done in this demo, but I'm not going to specifically address. For the DMA, well, this pretty much looks like this. So I create this little VI. All we're doing is asking all data from the memory. So we're asking how many items are remaining, and then we're grabbing the needed elements. This is a bit more complex though, but feel free to play around with this in the demo, or if you have any questions on this, you can look at it afterwards. Next up, offloading to the CPU. So we discussed that offloading to the FPGA has a lot of benefits. The FPGA can do things very fast. It can do a lot of things in parallel. But sometimes we just have to offload things to the CPU. So this is mainly useful or mainly used when using floating point operations. So if we don't know where a decimal point is and it can shift all over the place, well, then we need to use this. Also, if we need to use memory, or if we need to use operations that use a lot of hardware resources when putting it on the FPGA, think of division, multiplication, stuff like that. And also if we are using a ton of memory, or if the memory changes. Because when you code the FPGA, most of the times you can't really change things that are on the bit file. Now, so you load data to the CPU from the FPGA, you do your operations, and afterwards you have two decisions to make. Either you can push it back to the FPGA to do something else with it, or you can keep it on the CPU. This is an example of the demo, and this is also something that's used a lot with neural networks, and it's called Softmax function. So Softmax function, it's, well, this formula. It's using exponentials, it's using divisions where we don't know how much we're dividing. We don't know what the decimal point is going to be, so this is a nightmare to put on the FPGA. If we're going to put it on there, it's going to take up a lot of resources. So this is a prime example of something you put on the FPGA. In this case, in this example, I'm loading data from the FPGA. I'm doing my operation, and I'm sending it to the HMI. So instead of burdening the FPGA with this many, with putting this on the FPGA itself, I'm just putting this on the CPU, which has dedicated hardware for floating points, which can do this a lot quicker. So this is a bit more zoomed in. This is actually the essence. So grab the data, do your computational task, and then do whatever what you want with it. Either send back to the CPU for another, in another thread, send back to the FPGA, send to the sensors, and in this case to the HMI. Maybe in the meantime, does anyone have any questions? Because I'm steamrolling through this. Many questions. Well, I can answer a couple in the meantime. Maybe in the meantime, the reason why I'm not pointing it to the latest elements or saying, okay, do it per data set is just for simplicity of this example. In real life, you would either keep all data sets or you just use the latest stack. But I'm also using this example as user groups. So they, just because there's a lot of mixed skills there, just to make things simple, I placed that there. So the essence of this screenshot is directly seen. Question, do you calculate activation functions CPU and multiplication in FPGAs? Yes and no. So multiplications, I'm doing them on the FPGA, and there's actually a point which I'm going to discuss later on how to optimize multiplications on the FPGA and even divisions on the FPGA. The activation functions, some of them I'm doing on the CPU. So in this case, Softmax is an activation function. I'm putting that on the CPU. But some activation functions, well, actually most of them are really, really well suited to just putting them on the FPGA and just letting them do their thing. Another question, have you considered implementing with Taylor approximation and IP integration nodes, HSL and FPGA directly? I have considered it. Offloading CPU is paying a lot of latency anyways. I have considered it, but now this is a simple example, but this can be scaled up quite drastically. And also, Taylor approximation and so on, they take up a bit more resources than I like, especially when looking at hundreds of neurons in FPGA. Comment please on size of neural networks and needed size of FPGAs. It just depends on your FPGA and how you optimize it. But that part, let's keep that for after the presentation. I'm going to continue now with the presentation. So next up, scalability. So as already stated, we need to optimize our neural networks, or I had to optimize the neural networks to fit on the FPGA. And so a lot of things that came out of there I put in this part of the presentation. So I'm going to look at size considerations, which is pretty standard, and also at dynamic codes, how to change the behavior of our FPGA on the go, and to optimize our hardware resources. Scalability, I split it up in 3 elements: data types, operations, and parallelizability. Data types is quite straightforward. So the bigger the data type, the more wires we have on our FPGA, more places, or the more room it's going to take on the FPGA. So for example, I made a little example of the impact of the sizes. So I'm using a lot of fixed points within my networks, where I'm programmatically putting the fixed points during programming time or during compilation time. So when we have bigger fixed points, I'm just getting an error. I'm using, in this case, 104% of my slice LUTs. And by just reducing the fixed points to a more optimal size, I'm using suddenly a third of the slice registers, sorry, pardon me. So I'm using 83.3% of the slice LUTs. This is something you need to consider. So do you want to lose accuracy to benefit the size? So you can reduce the accuracy and you can put a lot more stuff on your FPGA without actually buying a new FPGA or an extra FPGA or a bigger one. Next up, size of operations. So this is actually interesting for the multiplication question. So up to here, most people will already recognize it. So multiplication or division, which is binary specific, is really cheap on the FPGA. It takes no resources at all. It's just a bit shift. It's literally losing some wires and adding some at the end, and you're shifting your bit values left or right. Next up, with Boolean logic, they actually use hardware resources, but they don't use that many. Same for addition and subtraction. They're close to Boolean logic. Most of the time, they use a little bit more Boolean logic than just plain Boolean logic. Next up, we have multiplication and division, which is numerically specific. So while we have binary specific, where we're just doing bit shift, when doing a numeric specific multiplication, what we're actually doing is, well, we're taking a lot of different bit shifts and we're combining them to get the actual multiplication that we need. So this allows us to do multiplications and divisions with much more accuracy. The only caveat here is constant. So during compilation time, when I make my neural network, I'm deciding my coefficients, my multiplications, and then I'm optimizing those values and then putting them on the FPGA as bit shifts, which I add. Where in this case, this operation is actually as expensive as just doing simple addition, because we just do bit shifts, which take no resources at all, and then we do an addition. Next up, we have accumulated calculations and multiplication and division, which are more generic variants. They take up a lot more resources, just because during compilation time you don't know the scope of their usage, so they need to account for much more. How should I say it? Much more flexibility. So most of the time, stick to this, but this is a neat way I found to actually put multiplications on the FPGA with a lot of accuracy. And I can also quickly show a neuron again. Now this might actually become a lot more clear. As you can see here, I'm just doing a ton of bit shifts. I'm doing a lot of divisions, but all in all, if I run this continuously, oh, sorry, I forgot to put it on simulation. I'll do that after the presentation. But yeah, so this is a combined division, so not just straight away bit shift divide by 2, divide by 4, divide by 8, but it's composition. But yeah, it's really cheap because we only have, in this case, 4 additions, and of course a feedback node because this is running in SCTL. So yeah, this is quite a cheap operation to do. Next up, parallelizability. So I already discussed FPGAs. They're great to do multiple things at the same time. But how can we decide what to do at the same time? We have a couple of different strategies depending on what we want. We can make code copies. So we can make direct copies. So just create a piece of code, copy paste it. We can make altered copies. So this is where we take a copy, we change some part of the calculation, and then placing it on the FPGA. In this case, that would mean all the coefficients, I would manually change them depending on the specific coefficients. However, in the larger framework, how it's built is pretty much the same. Now, by the way, I didn't do this. I automated that, so using PI scripting, which is one of the next points. Which brings me to code placement. So you can do it manually. Well, you can have mistakes. So when you alter it, maybe you miss something, and then it can take a long time to debug, especially if you do it with alterations. And every time you create something new, you need to do this. You can also automate it with PI scripting, which always gives the same results. You can make an infinite amount of copies, with the only limitation being your FPGA size itself. But, however, it takes a lot of development time. It took me a couple of weeks to get the algorithms fully up and running without bugs and without crashes. Which brings me on to the next part. So we can automate it using FPGA API scripting, which is normal API scripting, but it's really easy to make code way too big. And then when you compile it and suddenly you realize all this development for the FPGA API scripts or for the VI scripts, but suddenly it doesn't fit on any FPGA. Also, like I said, long development time, and also LabVIEW crashes. The LabVIEW crashes I found were due to, or happened whenever I try to access FPGA-specific objects, I/O nodes, clocks, memory items. So it took me a while to figure out a strategy to make sure that the crashes didn't happen, and it just meant staying away from those, just using normal VI objects or G objects, multiplication, for loops, while loops, feedback nodes, whatever. This is a pity. I hope NI fixes it soon, but I didn't really dig much deeper into it in the root cause, especially for my application. This was more than enough. But it's just something to watch out for whenever you use VI scripting for FPGAs. Tips and tricks, clean up references when you're done. I know there was a presentation on not doing that, except in certain cases. This is one of those cases. You will see your memory spike quite quickly if you forget to do that. Close your VI after done. I'm going to maximize that video in just a moment. I didn't do it in there just to show you, otherwise it would be just a boring photo of my desktop. Hide the block diagram. It makes the VI scripting go a lot faster, especially with large data sets. And something I also found, make sure your error handling is on point, because if you make a mistake after it's running for an hour, then suddenly it's a pain in the ass to figure out what went wrong, and you have no code at all afterwards. So this is the tool I made. It creates neural networks. So it does the optimization and so on. This part of the code, it just generates the neural networks to put on the FPGA. So as you can see here, I completely automated everything. So just telling VI scripting, hey, make this for me, making these addition trees, and so on. Okay, seeing we have 13 more minutes, so I'm quickly gonna move on to the next part. If there are any questions on this, let's keep them for the Q&A or the breakout session. Lastly, scalability, dynamic bit file loading. Now this is an interesting subject, which in my opinion is not talked enough about. So I'm going to discuss the strategy, batch processing using FPGAs, and the benefits they bring. So batch processing with FPGA accelerated computing means, well, you load a bit file, which does a certain computational task, but it can't do the complete computational task because you don't have enough hardware resources to do it. So what we can do is, well, we load a bit file, we load the raw data into the FPGA, we're doing our thing, and then we're loading the intermediate data. Once we did the entire stream, so once our big data set has been processed and we have our intermediate data set, we unload bit file 1, or our initial computational task, and we load in our secondary task. Then we push that intermediate data back in, and then we get our, in this case, final results. Of course, you can have as many steps as you want or need. Now, the benefit of this strategy is actually twofold. It's both cost-effective, and it also saves you some time if you implement it. It allows for smaller FPGAs. So let's say your customer doesn't have the money or is working on a really big scale, then it's quite easy to just go for a smaller FPGA, and if for some reason you need to have more processing, just load in bit files as you go. Also, it's easier to compile, so you're only altering one bit file. So instead of having one big thing that you need to recompile, you're just changing your one small bit file. Feel like changing or recompiling a certain VI instead of your entire project. Another benefit, let's need to optimize for size. So suddenly removing my entire spiel on size of an FPGA. So suddenly you can start looking at, okay, can I just nudge in a little floating points or make code more generic so instead of having those bit shifts which are really specific? Well, you can just put in multiplication, and then if the coefficients change, no worries. Another benefit is it allows for scalability. I didn't write it down, I forgot. But if you have multiple FPGAs, you can then load in bit files as resources are available. So if you have an FPGA, load in data, you can then load it to another, while two others are maybe doing something completely different. And suddenly when they're done, well, you can add the extra bit files to that chain, and then suddenly it can jump over. Suddenly making everything a lot more dynamic and utilizing our resources a lot more efficient. That brings me to my little MyRio example. So in this case, we have our adaptive cruise control, which suddenly changes to a traffic lights predictor. Now, this brings me also to the profile ID indicator, which actually shows you that the bit file has changed. So when it's showing 10, it's showing the adaptive cruise control. When changing it to traffic lights, it changes to 11, actually visually showing you that the bit file itself has changed. Because going back to the code, you can see this is hard-coded. Overhead on loading different bit files. It depends on a couple of different factors. The size of your FPGA, the speed of your memory, and the speed of your CPU. Just recognize that it's not instantaneous. There is going to be a couple of milliseconds, maybe seconds, that your resource is not doing anything. So that's also why I recommend using large sequential data sets for a batch process. So you're pushing up through a lot of data, doing everything at once, and then saving it instead of doing one data set or one data element, shifting the FPGA bit file and then doing the other. So yeah, I would recommend, depending on the hardware you have, to do a bit of experimenting to see what is going to be the most time efficient. Okay, so it's quite good. We have 8 minutes left. So we discussed in this presentation computational offloading both from the CPU to the FPGA and from the FPGA to the CPU. Scalability considerations, so size, computational tasks. We discussed FPGA API scripting, the things to watch out for, and yet we saw that it's really interesting and quite a time saver, especially with neural networks. And also we discussed batch processing, so suddenly how to make our static FPGAs a lot more dynamic. So thank you very much. Questions? Yes, indeed. So PCI Backplane, it allows for a lot more data to be transferred. So suddenly the entire dynamic will change. Maybe if you have a small FPGA on a PXI, it suddenly becomes a couple of milliseconds. However, I don't have the resources currently to test that. Well, thank you, Tom. Am I the right person to ask about neural networks? That's a good question. Well, the thing is, it's a changing subject. For example, I haven't worked on it in half a year. So, yeah, am I up to date with the latest developments? Absolutely not. I have a basic understanding, and my main focus was getting it up and running and optimized for the FPGA. Natan Nathan's might go for. Thank you. But yeah, like I said, I'm mainly focused on the framework itself. However, I'm currently working on expanding my knowledge on the usage of neural networks, both, for example, at visual applications, as well as deep learning applications. Well, okay. Let's discuss this maybe a little bit later. But if you guys want, well, let's discuss this later. I'll point you towards some resources I've used in order to, well, get a better understanding on the subject and actually learn how to use them instead of just seeing them as a magic black box that's where you throw data in and you suddenly get something out. Is it possible to communicate directly to the GPU via PCI from the FPGA? This is actually something I researched. Yes, it's possible. However, I've yet to try it from LabVIEW. I found a couple of dissertations that were discussing the subject that gave actual numbers. So yes, it is possible. However, I've yet to see someone actually show code which does it. So gradient descent, it's unfortunately, well, it is possible at the FPGA, but it will take up a lot more resources because your coefficients are constantly changing. While here, what I'm actually doing is I'm training it on my computer. Then afterwards, when I'm done, I'm actually creating my LabVIEW code, creating the constants that you saw, and then compiling them as a bit file. However, I've been playing with the idea actually doing it inline, where the target, where the CPU that's controlling the FPGA in the meantime is also gathering data to create an updated neural network to then override the bit file once a better bit file or better neural network has been created with more up-to-date data in the stream. But this is something way into the future which I might attempt. However, I've yet to actually attempt it. But I know it's possible. There are a ton of strategies about it, but without bit files. If I were a LabVIEW primitive, what would you be? Well, given I did an all-nighter, I would say a Boolean. Just the simplest of simplest. Any other questions? Okay, given we have 2 more minutes, I would say I'll move to the breakout room. Anyone that has any questions, remarks, wants to know more, wants to shout at me for doing bad coding, let's move to there. Thank you, everyone.